So, this is a simulation of circuits, lot of analog circuits for example, right. So, maybe there is an op amp, right, and under the op amp there might be a lot of different kinds of circuits like inverting amplifiers, non-inverting amplifiers, differential amplifiers and so on, right. So, let us say we have an inverting amplifier. So, if you apply a sinusoidal waveform, the output may be this sinusoidal waveform. Okay. So, you can see that the input has a maximum value of 5 volts and here the gain of this amplifier is minus 3, right. So, you may remember the formula minus R2 by R1. So, in this case it is minus 3. So, you can see that the output is having a phase shift of 180, right. When this reaches its positive peak, this reaches its negative peak and there is a gain of minus 3, right. You can also stop the simulation and observe. So, you may be curious to know what is the impact of changing this value. Okay. So, suppose this has a 10% variation. It may become 3.3 K and maybe this becomes double click here. So, maybe it becomes 0.9 K. Okay. So, this is 900 ohms and 3.3 K ohms. So, now if you run this guy, okay, see now you have seen that there is a distortion here, okay, because the output cannot go beyond 15 volts. The op amp, okay, let me stop the simulation and show you. This op amp has a peak value of plus 15 volts and minus 15 volts. So, if you exceed that value of, you will see distortion gets created. Okay, it is sort of clipping here. So, variation of resistor will bring about possibly such distortion in the waveform. Okay. Similarly, let us look at maybe some oscillators, maybe relaxation oscillator. Okay. So, again you can see that the frequency of this waveform is around 112 to 113 hertz. Okay. Any variation in temperature will cause the frequency to change because things like resistance are a function of temperature and the resistance and this capacitance play a very crucial role. If let us say this particular these resistance have some tolerance, so this became higher, this also became higher, this also became higher. and there was a variation in this capacitance also, it was 390 nanofarads. So, now you will see that the frequency here was 113. So, let us see what happens now. Okay. So, you will see that it has been impacted. Okay. It has been impacted, it has sort of gone down, right. You can even listen to the audio output. Okay. You could have also, without modifying, you can. So, it is a way of finding out how things change. See, if there is a catastrophic fault such as this is missing, then you will see the output will be very different. Let us try a different fault. Oops, sorry. See, the output has changed completely. Okay. So, if you play this audio, the frequency has really increased. Okay. So, you can see how things change. What if let us say there is a catastrophic fault where this resistance gets cut off. Okay. Again you can see the output has changed. Okay. So, you should understand that the difference in analog testing is, see, it is not so much about catastrophic faults, it is more about understanding whether it meets our requirements. This may be an audio amplifier or something like that. Let us look at whether they have audio amplifiers also. So, here is a difference amplifier. Okay. So, we can run the, so this is the difference amplifier. And you can use this simulator to figure out how it sort of work, what will be the parameters that it will provide when let us say resistances change, when the op amps parameters change. So, we can use this Falstad simulator to understand things like that. Okay. So, all right. Unfortunately, this does not provide measurements of things like FFT and things like that. Okay. So, you cannot, this is not used for measurement, so to say. You can look at the waveforms, but then you cannot do the FFT of these waveforms, etc. here. So, we will have to use a different tool for that.